Okay, so the first speaker is Gigi Rolandi from CERN, who is talking about status and prospects of the LHC machine experiment.
Do you hear me? Okay. So, good morning, everybody. It's a pleasure to be here with you, and thanks organizer for inviting me to give this talk. LHC is a fantastic machine, long work of many people, large investment, and it's a pleasure to tell you where we are. What you see here is the beautiful view of the Geneva Lake, the Alps, and the footprint of the X-LEP ring. You don't see anymore the 4-LEP experiment, but the logos of the 4 LHC experiment. So LHC is now in its final installation and commissioning phase. If you walk inside the tunnel, you see the strings of magnet mounted, and you see what you see there is the small train that brings equipment on the side of the magnets. And LHC is a two-ring superconducting proton-proton collider, and it is housed in 27-kilometer long LEP tunnel. And as you know, it's designed to provide proton-proton collision with unprecedented luminosity of 10 to the 34 at the center of mass energy of 14 TeV. In order to reach the required energy in the existing tunnel, the dipoles, and this is the main technological achievement, must operate at 1.9 Kelvin in superfluid helium. So the challenge of LHC essentially, compared to other machines, is that the magnetic field is 1.5 times larger. The luminosity for hadron machine will be 20 times larger. The collimation efficiency, that is in how much energy of the beam we can lose in the dipoles, and this is the point. They are cold and they don't want to get heat. The collimation efficiency must go from 70 to 96%. This is a big technological step, very difficult. And the beam stored energy will be 300 megajoule per beam. And when you have to deal, you're in the control room, and you know that if you do something wrong, you lose even a small fraction, 10 to the minus 6 of that beam will damage the machine in a very important way. You must understand what you are doing. The very good news is that all the magnets are in the tunnel. So this was achieved essentially in March this year, and they are all installed. Actually, few of them, as you will see later, have been taken out for repairs. And those magnets went on a very difficult quality control program, very complex. Since these magnets are superconducting, the magnetic field precision, I mean the number of multipoles you have in the dipole, that tell you how much current you can put inside the machine. I mean, the amount of proton per bunch is limited by how good is your magnetic field. And since they are superconducting, the magnetic field is given by the position of the cable, not by how well you can mill the poles on a numeric control machine. So the very tight specifications have been given in the precision how you put the superconducting cable in the what we call cold mass. And these are results of the measurement. I mean, here you see, I don't know what I have to do with that. Thank you. Here you see, I mean, how stable is the field magnet per magnet. This is the ratio between Tesla meters and kiloamps. And here is something that tells you how good is the field. I mean, how well the particle bend when they go through the field, if they come out exactly along the axis. And you see that the specification have been fulfilled. This is an important accident we had in the tunnel in March when we were testing the triplet. The triplet is the last 3 quads that are before the interaction region that squeeze the beam in order to achieve high luminosity. And during this test, essentially an engineering mistake was found on the magnet that could not be found with a single magnet. It was the set of 3 magnets, the asymmetry given by the fact that one magnet is the first of the string And essentially what you see here is the damage that happened to this magnet, and essentially this magnet that is a few tons moved by some 10 centimeters back under the effect of the magnetic field forces, and this is the so action had to be taken, and a new design has been validated, and now is applied in the tunnel to all triplets, but from the two magnets that have been damaged, that now they are now in the lab for repair. So this is a re-engineering of those magnets that have to be opened. The cold mass is okay, so this is the important point, but the new fixation points have to be put between the cold mass and the external part of the magnets. This will induce some delay in the schedule. There are 1,250 magnets, dipoles, and then quads also, so 2,000 magnets inside the machine. Which one? Do you hear me again? And when you put, they are connected in strings, and when you put the magnet together, there are a huge number of connections. Now these look trivial, but these are welding done on aluminum, and usually it's one shot. So you need it's a craft work. You need very careful welders. And this is going now for all the magnets that are in the tunnel, and here you see the progress. What you don't see is the derivative of this effect, but I can tell you that the beginning of the year this was at the level of 50–40%, and now all sectors are close to be completed. This is a very important step. Okay, now I told you that those magnets have to work at 1.9 Kelvin. This is not trivial at all. You have to have 1.9 Kelvin on the 27 kilometers of the ring, and essentially you have to understand that the internal part of the magnet is just in a bath of cold helium. I mean, there is contact between, it's like you take the cold mass, you put inside helium, inside the liquid. And in order to produce this cold helium, there is a lot of installation. Actually, this is a factor 10 to the 2 in dimension of cryogenic installation compared to previous plants. And essentially there are 32 megawatt of electric power that are needed, and in order to cool LHC you need 10,000 tons of liquid nitrogen. Keep in mind that one truck is 20 tons. So 10,000 tons of liquid nitrogen just to go down to liquid nitrogen temperature. You need 100 tons of helium and something like 5,000 cubic meter of water per hour. And all this goes inside the cryogenic system. And we have cooled down the first sector without the triplet. This was taken out because it was damaged. But this is only % of the part of the magnets. And you see, to go from room temperature to 80 Kelvin with liquid nitrogen, it took 1,200 tons of liquid nitrogen. This for 1/8 of the tunnel. So 60 trucks of 20 tons. And it took 3 weeks to cool down the first sector. From 80 Kelvin to 4.2, we cool down with the refrigerator, is 4,700 tons of material, and this took other 3 weeks. And then from 4.2 to 1.9 with the cold compression of 50 millibar, it took 4 days. And here you see the story of this cooling. It took overall 3 months. And what you see here in blue is the supply temperature, and what you see here in green, what you want to see is the magnet temperature. And we learned a lot. I mean, the engineers tell me that all these spikes are due to bad understanding of the control system of the refrigeration, the slow control that they are fixing now. All this wiggle should not exist. So, as usual, the first try is always to learn a lot. But the bottom line is that it takes 3 months. This is what it was foreseen. But this tells you how important is this number in the operation of the machine. If you have an accident, I mean, and you have to warm up a sector, you know already that you need 3 months to cool it down. Maybe this can be reduced to 2 months, but it's not a question of a few days. And what you see in this colorful picture is the going down in temperature in the last 4 days to the 1.9 Kelvin, and you see that the temperature was nicely uniform all along the string. You see the edge effects here, but you see that they eventually got 1.9 Kelvin all along the string, and this is very good. So, bottom line, procurement problems on the remaining component is now settled. We have all in hand in a way that is satisfactory. There is good progress of installation and interconnection work proceeding at high pace in the tunnel. There are numerous non-conformities intercepted by the QA program, and this good intercept, but it's also a fact that results in added work and time. Technical solution has been found for this inner triplet problem, but the repair of already installed magnet will induce significant delays that are taken into account in the schedule that I will show you now. And commissioning of the first sector can proceed by isolating the first triplet, but it will have to be redone with the triplet repair, needing additional warm-up down cycles. The first sector was cooled down to nominal temperature and was operated with superfluid helium. Heating problem with cold compression operation have now been fixed, and the power test can now proceed. Actually, this is a 2-week-old transparency. The first power test in this sector have started and are all good. So the engineering run that was already originally foreseen at the end of this year is now precluded by delays and installation of equipment commissioning. The 450 GV operation is now part of the nominal setting up procedure for beam commissioning to high energy. The general schedule has been reassessed, accounting for inner triplet repairs and their impact on sector commissioning. So all technical system commissioned to 70 the operation, and the machine will be closed in April 2008. The beam commissioning starts in May 2008. The D-Day is the 22nd of May, the first beam inside the LHC. First collision at 14 TeV in July 2008, and the pilot run will go up to 156 bunch, reaching 10 to the 32 by the end of 2008. 10 to the 32 is what we will achieve at the end of next year, to be compared with 10 to the 34, that is the design luminosity. No provision in success-oriented schedule for medium shape. I mean, if we have to have additional warm-up and cool-down, it will take months, cannot be reabsorbed easily. So this colorful picture shows you the schedule, and essentially this bar here on the side is when this inner triplet have to be reconnected. You have to understand that there is one inner triplet on each side of the experiment. So overall there are 8 triplets that have to be repaired. And what you see here, when you see 2 blue parts, blue is the cool down. This is the cool down of the sector that I've shown you a few seconds ago. And so you see that this sector, for example, has to be warmed up and then has to be cooled down again. So this is the schedule of various sectors. You see that there is a lot of parallel work at this point, but the engineers seem confident they can do. And this line here, you see, is on the 22nd of May, and tells you that the beam will go in for the first time inside LHC. What is important for the experiment is this day, where the middle of March, when the beam pipes must be installed and backed out inside the experiments. And so now the experiment have reassessed their schedule in order to be compatible with that, and fixing up some problems that they have. So the experiments are generally in good shape because they were ready to be ready in November, more or less. And now the fact that they have 3 months more, they take a big breath and they are happy, and they are now installing cables more easily. As you know, there are two big experiments that I've decided to show in this picture that is really not aesthetical, because the two experiments have very different dimension due to their different way of detecting muons. CMS is compact, has a very strong solenoid for Tesla magnetic field, and bends muons in the XY plane, so in the plane perpendicular to the transparency, while Atlas bends particles in the RZ plane and needs a lot of lever arm, especially in the forward direction, to measure correctly the momentum of the muons. In this nice picture, you see CMS central part lowering 2,500 tons that went down by 100 meters. This was one of the 11 parts of CMS that are being lowered, and this was a sort of mediatic event where many people were there. It's me with my son here that you don't recognize. But this was marked an important point, because when CMS is done by 11 parts, those 11 parts, the central one is the one that is fixed, because all the cables that go to the electronics do not move. So going down with the central part was a very important milestone for the project that was achieved with somewhat small delay. You see here the toroid of Atlas, you see the scale. This is the small toroid of Atlas, one of the two end cap toroid that was built in the West Hall at CERN, and then went by truck with a big transport to just in phase 2.1. And you see here this small object installed inside Atlas, so this you can have the dimension. Atlas is as high as 30 meters, I mean, it's like a big building. Here you see the Atlas inner detector being commissioned. This is the beam pipe, and this is part of the pixel detector that they are preparing to be installed inside the experiment at the end of June, so in these days. And here you see the CMS tracker that is in the lab, will be installed in November. What you see here is a track with the cosmic rays, and when you don't see is simply because only a fraction of the electronics is installed on the tracker. What also you do not see is the fact that this pipe is only 20% of the electronics. These are 2 million channels that are open at this moment, and you don't see dots, but from the aligned one given by the cosmic muon. This is an important achievement, because it's, I mean, when you have 10 million channels, you open the eye and they are all silent, means that you achieved a very good signal to noise. And also you see the quality of this instrument is fantastic. It's 99.8% working strips. What you see here is a picture of the pixel detector of CMS that is also ready. Here you see the side A of Atlas with the end cap calorimeter partially installed. You see here in this picture, you see very well the toroid, the 8 coils of the toroidal field of Atlas. These are the muon chambers. Here you see the central part of CMS. We're installing the last module of the calorimeter. Yes, it fits, it just slides in as foreseen. And you see here from inside the 18 modules of the calorimeter. And here is how well we know the calibration at day 0 of those modules. Here you see huge chambers in Atlas at the end of the experimental area, the big wheels. They are all chambers in Atlas are inserted, and but from very few for access. And here you see, for example, cosmic ray going through this part of the Atlas chambers. You see the hits in the various tubes that these are interested by the cosmic ray. And here you see a plot of the drift time. I mean, just the shape of the tube, and that is exactly as you foresee for a flat distribution that you achieve with the cosmic rays. Here is one wheel of CMS that is still upstairs. We will put the last part, the last half of CMS down in the pit at the last moment, because we have more room to work. The pit is much more tight than upstairs, and you see that the commissioning goes very well, and you see here MUON tracks measured by each of those chambers. So, experiment will be ready and will be working with quite a knowledge, and what is important is how the machine will start. And as I said before, the goal is to go to 156 times 156 at the end, during the first year, and to achieve a luminosity of 10 to the 32. And the idea is to establish colliding beam as quickly as possible, safely, without compromising further progress, means without damage to the machine. The path from the startup to 156 times 156, why this 156? Because at full luminosity there will be 2,500 bunches in each beam, but 156, the bunch are far apart, so you have not to cross at an angle, and for the machine physicist to cross at an angle is much more difficult than to cross straight on. So we postpone the testing of the angle crossing at a later stage, and this is the path. I don't know how many days will correspond to each line, but here you have a feeling of how much luminosity, integrated luminosity we can get. I have assumed 20% efficiency respect to the wall clock, because this is what happened at LEP, and it will be similar. So you see that near the end of the period, we will achieve some 30-60 inverse picobarn per month. So we will go through it in a few months, and I think at the end of the year we will achieve some, say, 100 inverse picobarn. But at the beginning we will start soon to see a lot of data, because the cross-section for minimum bias is very large, and what you see here could be the first 30 days of LHC, and this tells you how many events we collect for different categories, and you see that the good calibration candles like Z to leptons, we get a few tens, but minimum bias we get billions. So it's it will be, there will be a lot of events to understand and commission the detectors. So the first months will be very important, because using those minimum bias events we can do our first step in calibrating the detector. For example, we perform the first alignment, we will perform the first calibrations, and we will do the first studies of the detector. And also we can do the first QCD measurements, like jet cross-section and the feature of minimum bias events. For example, you see the minimum bias are important because they are overlaid to normal events when we run at high luminosity, and there is an uncertainty of the order of 20% on what is the multiplicity in minimum bias events. That this can be achieved in the first days of LHC. And also jet cross-section we have plenty, but this tells you what is the luminosity that you need to get 10 events above the threshold. So you need one inverse picobarn, then you will get 10 events above 1800, and 10 inverse picobarn you get 10 events above 3000. So you see that at the end of the run we will go clearly in the non-explored region, but in the first days we'll still be in this part here. And these events in the first part I was telling you will be used to calibrate the detector. What is the calibration we can achieve at day zero? Quite good already. We have tested all the calorimeter with cosmic rays, and as you've seen from the picture, this testing is something that continues and continues and continues. So, for example, the uniformity of the calorimeters will be at the order between 1 and 3%. The electron energy scale will be known to some 2%. So this means that when we measure an electron to 2%, we can tell the energy of this electron was exactly that. On the charger track, CMS is in much better shape than Atlas because of the magnetic field. It's much easier in CMS, is one number. Atlas, they have to study a map. But, I mean, I think that at the level of 4 or 5% will be known by both experiments pretty soon. And then those events will be used, like single pions, QCD jets, will be used with minimum bias events, will be used at the beginning to improve on the quality of the calibration. So I told you that we will collect in the first year some 100 inverse picobarn, and so this will be the luminosity span that we will get, depending how good will be the machine. Maybe 2, maybe 3 inverse, 100 of inverse picobarns. And so this is the rate of W, Z, and top events we will collect. Essentially, these are number of events similar to what the Tevatron has today. So we can say that at the end of the year, in the first year, we will have achieved as many events in W, Z, and top as the Tevatron has collected in its story. And so things that we will do for sure with this luminosity, we'll measure W and Z cross-section, we'll constrain a bit the PDF, especially the gluon one. We will see the top. For example, this is a plot where we show that you can see the top without tagging and just triggering on lepton and selecting events with exactly for jets. So very tight condition, but you see the top. This is important because we know the mass of the top, and we will use those events to get the energy scale of the calorimeters. So it's important to the other way around. And we will clearly start to look at what happens if there is something new. So this is a plot to show you what is the potentiality in 100 inverse picobarn for a new plasma minus pair. I mean, similar for a new plasma minus pair. Essentially, you see, in this experiment, what you have to do is to find the Drellian. So the Drellian cross-section is going down, and then if there is something at the level of mass, say 1 TeV or more, this is well distinguished about the background. So what you must do experimentally is to be sure that when you measure 1 TeV, it's not 400 GeV. And this is, for example, in CMS can be easily achieved, also in Atlas. Look at the scale, 100 inverse picobar, these are 2 events per 50 GeV. So you will have a few events, say 10 events in the case that is in this study. Which case is this study? I mean, this is those various models that have been studied corresponds to sigma time branching ratio at 1 TeV between 0.35 and 0.75 picobar. So that with 100 inverse picobar multiplied by the efficiency, you get some 10 events in the interesting region. And so you see that depending on the model, you are able to constrain the masses, to discover masses between 1 and 1.8 TeV corresponding to this sigma time branching ratio that is the relevant quantity for setting the discovery limit. Supersymmetry. Supersymmetry at low luminosity, its projection and cross-section are huge, for about 10 events per day even at this very low luminosity. And the problem is not so much the fact that we see them, but the fact that we have huge backgrounds, non-understood detectors. I mean, before saying that we have discovered something, we must have under control standard model. And the important question is how much luminosity we will need in order to say that we have the standard model under control. So otherwise, with 100 inverse picobarn, if the standard mode is under control and if we have understood the detector, we can explore already gluino masses at the level of 1.5 TeV. What do I mean by understanding the detector and the standard model? You see, this is a plot of missing energy. Missing energy is the prime quantity that you look at when you look for supersymmetry or for any other model that has a heavy particle that escape undetected. And you see that the rate of missing energy of half a TeV gluinos or squarks is huge. What you see in this plot, this is 100 events per 10 GeV. So means 1,000 events between 400 and 500 GeV. Missing energy. So huge rates, and this is what we foresee as standard model background. So if we are able to convince ourselves, for example, studying events where you produce, say, important source of background is Z into 2 neutrinos. You measure Z into 2 muons, and then so you know that you can trust your Monte Carlo on Z into the neutrinos. But this is not the only story. And what we will have to fight as startup will be with something like that. Look at this plot. This is the missing energy measured in D0, and the lightest one is the true one. But before you reach that, you have to understand how your detector behaves in time. Have I understood, do I have noisy cells? Noisy cells have to produce missing energy, because you may measure 300 GV in one cell because of noise, and this corresponds to minus 300 GV on the other side. Or I have a jet in a region that is not instrumented. When the jet goes there, his companion on the other side is not balanced, again producing missing energy. So we have to go through this work in understanding all the tails of the distribution, and then we will be able to understand correctly our missing energy plot. So this depends how the detectors will be. And now they are essentially, we will know it at startup. In March we will know, because we will have seen the noise plots, we will have seen how many channels are working. For the moment the situation is pretty good, much better than detectors I've seen previously, but one has to go through the whole run. Standard model Higgs boson search. You see that this is the combined discovery and exclusion plot for ATLAS and CMS combined, and this is 100 inverse picobar. So at the level of 100 inverse picobar we will not touch this physics, but what you have to do is to watch the Tevatron, because Tevatron is doing very well, and this is the observed and expected limit for D0 and the CDF these days. One corresponds to standard model, and this is what they plot is the ratio between what they exclude and the standard model cross-section. So you see they are approaching the standard model in this region, and with some luck they can explore a good fraction of the Higgs mass before LHC will start. So, conclusion. LHC now in its final installation phase, still a lot of commissioning work to be done, major hardware system already tested, so we look forward with confidence to first beam in May 2008. ATLAS and CMS are also in their final installation commissioning phase, all subsystems are tested with cosmic rays. LHC startup will not happen overnight. It may take some time to get the confidence that 300 megajoule beams can be routinely operated, and this will take time in the control room. And I expect a few 100 inverse picobar before the end of 2008, still low, but sufficient for a first glance on new horizons opened by this very powerful accelerator. And I want to conclude this talk saying, maybe when we switch we find something completely new and different. LHC will start, the first day we will collect 2 inverse microbar, and soon after, when we put 43 bunches in the machine, we go at 6 inverse nanobar per day. We'll be able to see soon if there is something with a cross-section large enough to produce large rate of events. Or say one thing that you find in the literature is like micro backcore production. These are very spectacular events, very spherical, that can have cross-section of 100 nanobar. And I think yes. The quality of the detector that I have seen these days is such that when we start we get something new, it will not take months to say yes, we have seen something new. And this is transparency I've just done, just to tell you how LHC will start. You see, the first day we will collect 2 inverse microbar. When going with one bunch, we're against one bunch inside the machine, and so we will be at this level. You see, minimum bias will be already a lot. This is the one event level. So minimum bias will be already a lot, will be in the level of many thousand, and millions. And then the first week we will reach the 6 nanobar per day. And then go down, it will take a lot of time. But so this is the level where we will start. Okay, thank you.
Yes, Maria Jose.
Yeah, it's a question regarding the Higgs. If I understood correctly, you meant that, for instance, if the standard model Higgs is between 110 and 120, for instance, that everybody is expecting that, Tevatron will discover first the Higgs? Did you mean that?
No, I didn't mean that. I mean that what I meant is that given their curves, in the region of 160, they will reach first before LHC. This is what I meant.
No, but my question is, imagine the Higgs is 117, for instance.
No, I mean, look, what...
Regarding luminosity, I missed the point.
Look at what are their expected curve with one inverse phantom barn. They, at 160, they are a factor 4 above the standard model. So they, increasing luminosity from 1 to 7, 8, they will arrive here. They will arrive to 1, so they will be able to have the say, likely to exclude the Higgs at that region. This I do not know. Here they are a factor 8 above the standard model.
This is the region I meant.
So it's more difficult, yeah. I mean, Higgs is there, Aleph has seen it, so it's...
so they will be competitive somehow.
It will be competitive, sure. I mean, it's, I'm following this very closely. I mean, the first say will be here, much earlier than there.
Okay, thanks.
More questions? No more questions? Okay, so we thank our speaker again. Yes, before you leave for coffee, just a few